Hello everybody, and welcome back to another video on my channel. This is the final advanced trigonometry / geometry video, and this is actually not really covering any topics, any example, or any proof. This is just a very quick introduction to non-Euclidean geometry, and this is probably the most advanced presentation I have done on the history of this channel, and probably, in my opinion, will be one of the more advanced ones. I myself know very little about non-Euclidean geometry, and I had to do a ton of research to compile the slideshow together just to figure out who did what, where was everything. Of course, I knew a little bit about the origins of non-Euclidean geometry, about hyperbolic and elliptic geometry, but that will come later. But yeah, this is just an overview. This is more to just get you started and kind of ignite your curiosity. Now, this represents revolutionary developments in mathematics, and it challenges over 2,000 years of geometric understanding, possibly even more, if you account for the fact that ancient civilizations also knew a good amount of Euclidean geometry, or at least what is now known as Euclidean geometry. These are different types of geometries, basically kind of different types of spaces, and different types of curvatures based on axioms, kind of basically facts that you kind of are assuming to be true and kind of are like the foundation of everything. And this is actually very closely related to Euclidean geometry, but there are a few crucial modifications. The key difference is the treatment of parallel lines, and its significance is the foundation for understanding curved spaces, almost kind of like our universe or the world around us, as this universe is not in 2 dimensions. It is, at least as far as our scientific knowledge knows, in 3 spatial dimensions. So that's about it for the introduction. Is elucidates elements, or at least a little bit of historical context about it. This book was written around 300 BC, and the thing we are going to focus on is the 5th postulate, or the parallel postulate. Through a point not on a given line, there is exactly one line parallel to the given line. So this is basically a fancy way of saying is if we have a line, then we have another point. There's a line that's parallel to the other line through the points. It kind of seems very obvious at first, but many people were trying to prove it, but it's actually done over 2,000 years, but no one has really been able to prove it. And many proofs were accepted until errors were discovered. So many proofs that involve different types of geometric manipulations or using axioms normally had some mathematical error in them that the creator either forgot to overlook or just thought the community wouldn't care about. There are 3 main pioneers of non-Euclidean geometry. Carl Friedrich Gauss, which is the first one. He lived from 1777 to 1855. Many people say he is the greatest mathematical thinker since Newton, or Isaac Newton, who is the guy whose apple fell on his head and he suddenly created the law of gravitation. So, he began investigating the parallel postulate at 1792 at the age of 15 years old. He developed a lot of insights, but he never published because most likely he was concerned about reception of different ideas. If you looked at Galileo or other things like Copernicus, who, when they talked about the heliocentric view, were shunned by the Catholic Church and normally cast aside, and suffered many punishments for defying the state and the church. The second pioneer of the 3 pioneers is Nikolai Ivanovich Lobachevsky. Help me with that pronunciation, someone in the comments. Trust me, because I know what it feels like to have your name butchered, and I would not want that to happen to anyone. So I'm sorry. I know you're not alive right now, but I hope I didn't butcher your name, Nikolai. And someone in the comments, please correct me. And this person lived from 1792 to 1856. And he was a Russian mathematician, and some people, not many, call him the Copernicus of geometry. In 1829, he published the first account of non-Euclidean geometry. And as I said earlier, Gauss had many insights, but he never published. His key innovation was through a point, not on a line, infinitely many lines can be drawn parallel to the original line. This is actually one of the two types of non-Euclidean geometry, which is the major treatment of parallel lines, where is the key difference. And this type of non-Euclidean geometry, it was initially called imaginary geometry, as it felt like it was almost made up, it had no ground proof in reality, and was kind of like imaginary numbers until it proved itself with applications. The third of the three pioneers was János Bolyai, who lived from 1802 to 1860. He was a Hungarian mathematician working independently, without any team or a lot of apprentices. His famous quote is, "Out of nothing, I've created a strange new universe." In 1832, he published similar work to Lavoisier with a few differences that wasn't mentioned in the research that I did. And he actually developed a mathematical framework for hyperbolic geometry, which is basically one of the two non-Euclidean geometries that is covered. Riemann's contribution. There was a mathematician called Bernhard Riemann. You might know him for the Riemann hypothesis, which is a pretty kind of pop science or sci-fi type of topic, but it is a real problem to prove the Riemann hypothesis. And he also discovered elliptic geometry. His 1866 work generalized these concepts to higher dimensions, and his key principle was no parallel lines exist, all lines eventually intersect. And this is the other type of geometry or non-Euclidean geometry, which is elliptic geometry. His legacy is created the mathematical foundation for Einstein's general relativity. There is a special shape called the Saccherchi quadrilateral. Giovanni Germo Saccherchi, sorry if I butchered his name, from 1667 to 1773, he was an Italian Jesuit priest, and he attempted to prove elusive fifth postulate by a method called reductio ad absurdum, basically by assuming it was false and trying and showing that leads to contradictions in math. So if I want to prove 1 plus 1 is equal to 2, maybe I would count and let's say, alright, no, 1 plus 1 is not equal to 2. So if I count 1, 2, 3, but then if I count 1 and 1, it shows that they're not the same number. And of course, this is a very basic example, and it's kind of self-explanatory, similar to an axiom, but it does kind of get the basic point across of reductio ad absurdum. Now, the Saccherchi quadrilateral is two equal sides perpendicular to the base, and then of course there has to be a fourth side. And that derives many theorems of non-Euclidean geometry while seeking contradictions to a theorem in elusive fifth postulate, which is in Euclidean geometry. So it's kind of interesting how a book from more than 2,000 years ago is still relevant even now, and it kind of was the backbone of pretty much all non-Euclidean geometry as attempts to prove it were made. There are two main types of non-Euclidean geometry. These are based on the treatment of parallel lines and the curvature. Hyperbolic geometry is infinitely many lines go through a point parallel to a given line. So basically, there are infinitely many parallel lines. And lines called ultraparallels diverge from their common perpendicular. Elliptic geometry is the exact opposite. There are no parallel lines, and any two lines will eventually intersect. Now, curvature and triangle properties are another pretty big difference in different things about non-Euclidean geometry. In Euclidean geometry, the angles in a triangle adds up to exactly 180 degrees. In hyperbolic geometry, it adds up to slightly less than 180 degrees, and in elliptic geometry, it adds up to something greater than 180 degrees. So if Euclidean is 100%, hyperbolic is less than 100%, and elliptic is greater than 100%. Now, There are a few main curvature differences. Euclidean geometry is zero curvature, which is a flat space. Hyperbolic is constant negative curvature, which is saddle-shaped. And elliptic is a constant positive curvature, which is almost sphere-like or elliptoid-like. Here are a few mathematical models for hyperbolic geometry. First is the Poincaré disk model, created by Henry Poincaré in about 1880. It's basically saying that there is a hyperbolic plane as interior of some unit disk, and lines appear as circular arcs intersecting the boundary at the right angles. So it preserves angles, but it distorts distances, and in that sense, parallel lines as well. Now the second one, or the second two ones, are the Klein model and the upper half plane model. Klein model is hyperbolic lines appear as straight chords, basically kind of making it look very similar to Euclidean geometry. And the upper half plane is lines are vertical lines or semicircle with centers on the real axis. So that means that imaginary numbers are also used in the treatment of non-Euclidean geometry. I told you in some of my last videos, everything is connected, even though you might not realize it. Here are a few elliptic models, especially the pseudosphere, which is Eugenio Beltrami. Sorry if I butchered their name again. In about 1868, he published this. Now, this is a physical model for hyperbolic geometry, created by revolving a tractrix around its asymptote. So, what is a tractrix, you might ask? This is basically if I pull an object with a string, it's basically the curve the object's motion makes, and I know this is it's a very basic definition and it can get much more complicated, but that's about the gist of it. And it has a constant negative Gaussian curvature, which is a little different than the curvature as we know it, as I said that elliptic models have constant positive curvature instead of constant negative curvature. A few more elliptic geometry models is geometry takes place on a sphere surface. Many models use lines as great circles, and it is important for spherical navigation or augmented GPS systems. There are a few physics applications, especially in Einstein's theory of general relativity. Basically, the space-time model as a curved four-dimensional manifold, and see, when I said curved, that basically mentions non-Euclidean geometry, especially elliptic and hyperbolic. Then mass and energy cause a curvature in the space-time, and the Einstein field equations are formulated in this same non-Euclidean framework, which was developed over 100 years before Einstein himself created this theorem. At least a few of them were. Now, a famous quote by him, or not as much famous, but a quote by him crediting non-Euclidean geometry is, "To this interpretation of geometry, I attach great importance. For, should I have not been acquainted with it, I never would have been able to develop the theory of relativity." Of course, the applications don't end there. There are also cosmological applications, basically understanding the geometry of the entire universe. In Euclidean geometry, the universe is flat. In a closed universe, or with a positive curvature, it's elliptic geometry. And an open universe is negative curvature, or hyperbolic geometry. So modern cosmologists use these models to describe many possible universal geometries. But this is beyond the scope of this video. Of course, this is just an introduction. So I'm not going to cover this. Of course, I'm just giving you an overview of what it is and all the different applications. There are applications also in navigation and computer graphics. Now, the first one is in navigation and GPS technology. Traditional GPS relies mostly on Euclidean geometry for local navigation. But advanced navigation systems with pinpoint precision over huge distances or to account for curved surfaces require non-Euclidean approaches, especially elliptic geometries, as the Earth is a sphere. There's also in computer graphics, creating immersive virtual environments and animating things very well requires a study and a knowledge of non-Euclidean geometries. Also, complex patterns and tessellations in video games are pretty much impossible in Euclidean space. And that's why this universe is not flat. There are a few more advanced applications in non-Euclidean geometry. The first is something called topology. Topology is basically the study of curves and structures in multiple dimensions, and it is very interesting, although I don't know much about it. You can actually watch many videos online, especially from a channel called Veratizio or 3 Blue 1 Brown, 3B 1B. Those two channels have a ton of information about topology, and it's actually very interesting if you want to get into it. And also manifolds like the Klein bottle, etc. Now the next application is the Minkowski space, which is used in special relativity. This is the four-dimensional space-time representation, and the distance function distinguishes time from space coordinates. This was basically pretty much the space that Einstein used to develop his major theorems. There are a few contemporary research areas that are still being researched today. These include geometric analysis and curvature properties, the Gauss-Bonnet theorem, connecting geometry and topology, which I genuinely think that topology is actually kind of similar to geometry, but mathematically they are quite different. String theory and quantum field theory applications use non-Euclidean geometry, and network analysis and graph visualization using hyperbolic space for stuff like radios or more advanced than radios, but that's basically how it works. There are so many revolutionary changes and impact that non-Euclidean geometry has done. First, it transformed geometry from physical space description to an abstract mathematical discipline, but it actually ended up having many applications which were not foresaw back then. And it liberated mathematics from just intuitive spatial reasoning, such as a different set of axioms, and this kind of constrained our own study of the universe, and it kind of opened up a whole new world of possibilities, and it created the foundation for modern theoretical physics. There is still a continued impact. Of course, it had physics foundation, it's essential for modern cosmology, it's essential for technology, and it's also essential for research in mathematical physics and computational tools, because if you didn't know, computers are getting better and better and better, and they require more advanced algorithms which could use non-Euclidean geometry, but also in designing things. This kind of liberates everything to have a more wide world view and to simulate our universe more clearly. Our conclusion is that this is one of the biggest shifts in mathematical history, and its impact extends far beyond pure mathematics, similar to imaginary numbers. This provides the mathematical foundation for Einstein's relativity theorems and modern cosmology. It has continued relevance in contemporary technology and research, basically meaning it's not done yet, and it's still at the frontier of everything we do today. This proves that profound discoveries, huge discoveries, entire like universe-shifting discoveries almost, these come from questioning the most basic assumptions that common sense says should be true. Thank you so much for enjoying this video. I hope you're happy with the 5 video upload this week. I hope I made up for my dormancy in these past few weeks. I was busy and I decided to make up for it for completing 2 series, or almost like striking down 2 birds with 1 stone. Please make sure to like, subscribe, and hit that notification button for more awesome updates like this, and comment down below any suggestions so I can create new videos, create better videos for you so you can learn more. See you in the next one. Bye-bye, and have a good time.